Hey guys, welcome back to another video, and today we're going to be solving the LeetCode question largest component size by common factor. Alright, so in this question we're given a non-empty array of unique positive integers a. Consider the following graph. So there are a.length nodes, so the number of nodes are the same as the length of our array a, and they're labeled starting from 0 all the way to the length minus 1. So if we have 10 nodes, if we have a length of 10 for our array, we're going to have a total of n nodes labeled from 0 through 9. Okay, and there is an edge between ai and aj if and only if ai and aj share a common factor greater than 1. Return the size of the largest connected component in the graph. So let's take a look at example 2 over here. So we have 20, 15, 9, and 63. So over here we have one graph with 20 and 50 connected to each other. So the reason they're connected is because they have several factors other than just one. So they have 2, they have 10, and 5, and so on and so forth. Okay, and over here for 9 and 63, they're not connected to 20 or 50 because neither of them share the same factors. Whereas 9 and 63 themselves share their own same factors, which in this case is the number 3. So that's how we're going to get it. And in this case, they both have the same length, so we're just going to output a length of 2. Over here, they're all connected. So let's see how that looks like. So 4 and 6. So in this case, we have 4 and 6. So 4 and 6 share a factor of 2. Then we have 6 and 15 sharing a factor of 3. And then we have 15 and 35, which share a factor of 5. So in that case, everything is connected. So we have an output of the number 4. All right, so let's see how we can solve this. So you can kind of split up our question into two parts. So one of them would be, what we're going to do is we're going to iterate through each of the numbers. So we're going to go through 4, 6, 15, and 35. And after iterating through them, each time we're going to get out all of its prime factors. And we're going to store it in such a way that for each index, we're going to have whatever its prime factors are. So in this case, for the index 0, its prime factor is going to be the number 2. And so on and so forth. We're going to do that for each and every number. So that's one part of the question. And the second part is, how do you take that information we just have and kind of make these numbers into separate groups or sets? So the answer to that is we're going to be using a union find data structure. So this data structure is basically used to keep track of different subsets that we might have and how they're kind of interconnected with each other. So I try to think of several ways to kind of explain this, but I came up with was this visualization from visualalgo.net. I'll put a link to this visualization down in the description, so do check it out. Okay, so let's start off. Our first step is going to be to initialize our data structure. So let's say this initialization is going to have the same length as whatever the length of the array is. So over here, let's assume that the length of our array is 10. So let's hit go, and what happens is we get a data structure with values from 0 through 9. So what you can kind of imagine is, so we have these data structure, these nodes, and each node is its own parent. So the parent of 0 is, well, 0. The parent of 4 is, well, 4. And one more thing you should notice is, let's say we go to the 5th index, so 0, 1, 2, 3, 4, 5. The value of what's at the 5th index is the index itself. So what do I mean by that? The 6th index has the value 6. The 1st index has the value 1, so on and so forth. Okay, so after this, there's two more functions that are important for us. Okay, so we kind of have two main functions that we have are the find function and the union function. So what the find function does over here, it basically finds whatever subset our set is in. So let's say we want to look for set 2, it's going to find whatever subset it is. So let's say we run this right now. In this case, we're just going to get the value. We're just going to get this value as it is, because as it is right now, each set is the root of itself. So it doesn't really matter. And after that, one more function that we really need is a union set function. So what this does, it makes one of the sets a subset of the other one. So instead of kind of talking about it, let me just show you what it does. So at I have 2, and at j, I have 0. So let's hit go. So first we find the value 2, okay? Now we found the value 0, and let's see what happens. So what happens is 2 becomes a subset of 0. So in this case, we're making, for 2, 0, we're making 2 the subset of 0. So you could have it do whatever, either way. So you could have 0 become a subset of 2. But in this case, we're just doing it like this. So let's just look at another example. So let's say union set, and now let's do it on 7 and 1. So let's hit go. So first we find 7, now we find 1, and now 7 is going to become a subset of 1. So just to show you what I was talking about earlier, now what we're going to do is let's do find set, but let's find the value of 2. Or let's find the subset 2. So what's going to happen is when you go to 2, first we go to 2, and then what we're going to do is we're going to recursively call until we reach the parent. So I'll just run that again. So find set and 2. So as you can see, first we go to 2, and afterwards we go back up to 0, since 0 is the parent. So similarly, let's say you do find set 7 is going to do the same thing. So first we go to 7, and then we go to its parent. Okay, so that's kind of how the find set function works. And let's just look at one more thing. So over here, let's say we have I is equal to 2, and let's say j is equal to 7. So let's hit go. So just to summarize what happened real quickly is we called union set 2, 7, and over here when we looked for the value 2, we found its parent, which is 0, and then for 7 we found its parent, which is 1. So now what happened is 7's parent, which is 1, made 2's parent its child. So in this case 1, and then we, as you can see, that's 7's parent, so that made 2's parent, which is 0, its child. So this is how it ended up looking like. And one final thing that I want to show you, let's say we do, actually going to end up getting 1. So that's just kind of what I wanted to show you. So we find the parent element. So what's happening over here is something called path compression. And in simple words, all it's doing is it's making our data structure or the search a lot faster. Okay, so previously to find the set 2, we actually ended up taking, I think, 4 steps. And now let's say we call the same thing again, so find set 2, and now it's only going to end up taking 2 steps. So 2, 1, there, done. So it just makes everything faster. Okay, so now let's try to actually implement this in our code. I'm not going to be going over it line by line, but I'll just kind of show you the overall picture of it. So over here, I'm first making our union find class. So in our union find class, we're first going to start off by creating our array, right? So in this case, the array is going to be, so if our length is 10, it's going to be 0 to 9. So that's what we're doing over here. So I for I in range n, and n is going to be the length of our array. Okay, and then afterwards, we're also going to be creating another array called size. So in the beginning, so what is this going to hold? It's going to hold the size of each of our sets. So in the beginning, they're all going to have a size of 1. And as we go down, we're going to change it accordingly. So over here, we have our find method. And what we're doing is we're first going to check if we're going to go to that x index. And if that the value at that index is equal to x, in that case, we're just going to end up returning it. If that is not the case, what we're going to do is we're going to call that function on that again. And that's going to help us find the parent. So we're going to keep calling this function on itself, so self.find, until we find the parent. And once that happens, once we do find what the parent is, and what we're going to end up doing over here is called path compression. So this is what we're doing here, and all that does, it helps us make our steps faster. And at the ending of this, we're going to return self.ufx, which is the parent. Okay, so, and after that, we have our union function. So our first step is to find the root or the parent of x, and then we need to find the root of y. So x and y, and now we're going to check if they're equal to each other. So if the x root and the y root are both the same, then in that case, it's already where, the sets are already where they're supposed to be. So we're just going to end up returning, and we're done with the function. And what we're doing here is we're making the x root the child of the y root. And what we're going to, after doing that, since what we really want is the size of each of these sets. And what we're going to do is we're going to go to our size array, which we defined over here. And we're going to add the size of the x root to it. And then we're going to go to the size of the x root and we're going to make it 0. And the reason for that is because the x root has become a child of our y root. Okay, so that's going to be it for our union find class. And now let's see how we can integrate this into our solution. Okay, so in our solution, we're going to start off by defining an empty dictionary, and we're also going to create an object of our union find, and we're going to give it the length of a because that's going to be the length of it. So what actually is the purpose of our dictionary? So the purpose of our dictionary is that it's going to store all of the prime values that we get, and it's going to, so that's going to be the key, and its values are going to be at what index do those prime values exist. So let's say we have a prime value 2, and let's say that exists at index 0, 4, and 5. So those are going to be its values. So that's what our dictionary is for. So before going into this over here, let's see how do we actually get the prime factors for each of our numbers in the array A. And for the code for getting the prime factors, I actually got that from Geeks for Geeks, which is another website, and I'll put the link to that in the description. Okay, so we're going to start off by having a set. So I just called it out for output, and this is going to be the set that we're going to that's going to hold all of the prime factors of this number. So what we're doing over here, think of this as the first step, and we're going to check if it's divisible by 2. And if it is divisible by 2, we're going to go inside of a while loop, and we're going to add the prime factor to our set. And each time we go inside of this while loop, we're going to divide our n value by 2. And we're going to keep going inside of this until our value is not even anymore. So if it's divisible by 2, we know it's even. So by the end of the step, our value is not going to be even. So it's going to end up being odd. So now our number is odd for sure. So we're going to end up going into a while loop where we're going to start off at the value 3, and we're going to go until the square root of n. And each time, and we're also going to be stepping by a value of 2. And the reason that we're stepping by a value of 2 is because after 3, all of the prime numbers have a gap of at least 2. So you could go by 1, but by stepping by 2, it just makes it a little bit faster. Okay, so each time we go inside, we're going to check if our value is divisible by whatever the I value is. And if it is, we're going to end up adding that to our output set. And we're also going to divide our number by that value. Okay, so once we're done with this for loop, we're going to end up with the final number. So in our prime factorization tree, it's either going to be 2 or 1, or it could be any other prime factor. So if it is less than 2, then in that case, we're just going to ignore it. And if it is not less than 2, then in that case, we're going to add whatever that prime factor is to our set. And finally, we're going to end up returning our output. So this gets us all the prime factors of a certain number. So that's what we're going to end up doing. So in this for loop over here, we're going to enumerate our list. And the reason for that is because we want to get the index. So we're going to do index, comma, each of the numbers. So at each iteration, we're going to first find all of the factors, prime factors, for our for that specific number in the array. So right now, for the first number, we're going to find all of its prime factors. So once we get all of its prime factors, it's going to be inside of our set, and now we're going to iterate through all of those. So over here, we're doing for prime and prime, so we're getting each of the prime numbers. And over here, we're going to check if our prime value is a key in our dictionary. Okay, so if it is, then in that case, what we're going to do is we're going to go to our union find object, and we're going to call the .union method. And we're going to call this method on our index, whatever index is there at the value of this prime number. So after doing this, if our prime value already exists in our dictionary, what we're going to do is we're going to change the key value to whatever our current index is. And if it does not already exist, then in that case, we're just going to add that key. Okay, so if this is a little bit confusing to understand, I'm going to try my best to draw this out. All right, so let's just go back to this example over here. So 4, 6, 15, and 35. So that's what I'm going to be performing our function on. So 4, 6, 15, and 35, that's our input array. And I'm sure this should really kind of get everything together, and I'm sure you should understand the question after looking at this. Okay, anyway, so after this, we have to define a few things. So we have our dictionary, which in the beginning is just going to be empty. So let's just have our empty dictionary. And we have two arrays. So we have a sizes array, right? And in the beginning, this has all ones. So everything has a size of 1 in the beginning. And the reason it has a length of 4 is, well, because our input has a length of 4 as well. And since our input has a length of 4, over here we're going to go to our union find data structure and let's define it. So when you initialize it, we're going to have 0, we're going to have 1, 2, and 3. So this also has a length of 4. So let's start off by doing the first thing, which is, well, we need to find the prime factors of 4 over here. And its prime factors are, well, it's only 2. So 1 and 2, but yeah, we're not going to count the 1, so 2. Okay, so now that we have 2, we're going to add this to our dictionary. So that's going to be 2 as a key, and its value is going to be whatever the index of the number 4. And its index is, well, 0. So you have 2, 0 as the key and the index. Okay, so now let's move on to our next iteration, and nothing over here changes for a size or for our union find. Okay, so in the next iteration, we have the value 6. And what are its prime factors? Well, we have 1, 2, and 3. Again, we're ignoring 1. Okay, so 2 and 3. So first we're going to go to our dictionary and see if 2 already exists. And the answer is 2 does exist. So what we're going to do is we're going to use the union function on 0, 1. And the reason it's 1, and now we're going to perform the union function on 1, 0. Okay, and the reason we're doing it on 1, 0 is because 1 is the index of 6 and 0 is the index 2 was at. Okay, so now that we have this, let's see how that looks like. So let me just draw it out. So normally, in this case, 1, 0. And if you go back to our function, 0 is becoming the parent, right? And 1 is becoming a subset of it. So just to kind of visualize it, we're going to have 0 and then we're going to have 1 coming off of it like that. But what we're doing is we're actually going to represent it in a slightly different manner. So what we're going to do is we're actually going to get rid of this, we're going to erase it, and we're going to change its value to 0. And what it's kind of telling us, so originally, or how you would visualize it, is 1 being a subset of 0. And what this is kind of telling us is at the first index, so the value 1, actually its parent is 0. So that's why we change this value to 0. One thing we're going to do is we're going to go to the first index and we're going to change this to 0. So for the size, so we're going to change this over here to 0. And before we do that, we're going to change the 0th index size to whatever its current size is, so 1 plus this size. So this was 1, so it becomes 1 plus 1, and now this has a size of 2. So you can keep going and kind of imagine how this changes. And let me just finish this iteration over here. So actually, currently our dictionary is 2, 0. And what's going to happen is going to get updated, and now it's going to be 2, 1. And one more thing we're going to do is, since 3 is not there, we're going to add that to our dictionary with the current index, which is, well, 1. So again, once you go to 15, what's going to end up happening is you're going to have 3, 5 as its prime factors. And over here, 3 already exists. So you're going to end up calling the union function. And we're going to call it on the current index of 0, 1, 2, and this index over here, which is, well, 1. So 2, 1, and what that's saying is that 2 is becoming a subset of 1. And in other words, 1 is becoming the parent. Okay, so when you're calling this union function, let's just kind of look at our first visualization and how would we kind of be like, so we had 0 and 1 was its child. And when you're doing this, 2 would be its other child. So that's how it will look normally. But over here, since we're doing this method, so 2, 1, so we're going to go to the second index and we're going to change it to have the value of whatever is at the first index. So now it's saying that 2 is actually a subset of the value 0. So we get rid of this, and now this is going to end up becoming 0. And simultaneously, what we do is we go to the second index here. We're going to make this 0, and we're going to add a value of 1 here, since this had a value of 1. And this ends up becoming 3. And if you do it for one more iteration, let's just do it actually. So this actually becomes 5 comma 7, and I didn't add everything here. So this let's see how our dictionary updates. So this stays as 2 1, and then it becomes 3 2, so 3 2, and then we end up having 5 2, and yeah, that's it. So 5 exists over here, and 5 already exists in our dictionary. So over here we're going to call our function on we're going to call it on this index, so 0 1 2 3, and we're going to call it on this index, which is 2. So we're calling our function on 3 comma 2. In simple words, this is going to end up changing to 0, and afterwards we go to the 0th index. This value becomes 4, and this value becomes 0. And just to show you what that looks like in our, as per our initial visualization, 0 is the parent root, with the children being 1, 2, and 3. So those are all of its children, and 0 currently has, so there's 4 elements over here. So how do we end up getting our final result? So all we're going to do is we're going to find the maximum value in our sizes array. So in this case, we have the values 4, 0, 0, 0, and obviously our maximum value is 4. So we're going to end up outputting 4. So if you look over here and you look at the output, it is 4. And yeah, so that's how it is. So I tried my best to explain it. I'm sorry if it was a little bit cluttered. Do let me know if you have any questions, and I will try my best to answer them. I'm not an expert in this. But anyways, as you can see, our submission is accepted. And finally, thanks a lot for watching, guys. Do let me know if you have any feedback. And don't forget to like and subscribe if this video helped you. Thank you.